Imagine the following scenario set in the not-too-distant future. Somewhere within the confines of NASA's Goddard Space Flight Center outside of Washington, D.C., a scientist from the Seismic Studies Office sits in front of her workstation to review observational data for several pre-selected geographic danger zones collected by a suite of Earth monitoring satellites. Running a program designed to establish background reference levels for the different instrument readings, she notices some anomalous fluctuations in the ionosphere above the San Francisco Bay region. In consultation with counterparts in Europe, Russia, and Asia, who are monitoring data from other satellites, NASA scientists are able to confirm a pattern of several anomalous readings around the San Andreas fault zone, including slight changes in ground level in some places and increased heating in the atmosphere. Over the next 36 hours, urgent efforts are coordinated with regional field offices of the U.S. Geological Survey, along with local university researchers, to examine on-the-ground measurements of microseismic activity, gaseous emissions, and strange animal behavior. By this time, an emergency management network within the federal government has been put on alert, coordinated by the National Security Council and involving local, state, and federal agencies prepared to implement contingency plans for evacuation and disaster response. The scientists, now working with international partners with expertise in all aspects of earthquake precursors, have determined that the signals point convincingly toward the coming of a major earthquake to strike within a 100-kilometer radius of San Francisco within 3 to 7 days. The President authorizes the Army Corps of Engineers to oversee the evacuation of the most vulnerable areas. A magnitude 8.0 earthquake hits within the forecast window. More powerful than the 1906 earthquake, it causes significant structural damage to certain buildings, roads, and other structures. But thanks to preparation and a swift response, the human toll is miraculously low. A natural disaster has struck, but a catastrophe has been averted. Had history taken a different turn over the last 40 years, this script, or something like it, could have been written for the March 11th earthquake and tsunami that destroyed whole stretches of Japan's northeastern coastline and killed more than 20,000 people. A number that surely would have been tens of thousands higher had Japan not already had the highest level of disaster preparedness of any country in the world. Whereas prediction was once the holy grail of seismology, in recent decades we've seen the study of earthquake precursors suppressed by establishment science. The ancient myth that mankind must live at the mercy of the great forces of nature seems to have gained the backing of authoritative scientific opinion. But, while certain politicians and scientists make excuses for what can't be done in the face of natural threats such as earthquakes, the scientific foundations for a short-term forecasting capability have already been laid. Consider the recent pre-publication release of a paper demonstrating an unmistakable pattern of atmospheric anomalies in the days leading up to the disaster in Japan. The authors, including Dimitar Uzanov of NASA's Goddard Space Flight Center and Sergei Pulanets of the Space Research Institute of the Russian Academy of Sciences, looked retrospectively at data on the state of the atmosphere and ionosphere above the epicenter of the magnitude 9 quake, leading up to and immediately after March 11th. Using 4 independent parameters, they looked at effects of atmospheric heating that they believe is caused by the release of radioactive radon gas around the fault zone surrounding the epicenter. Radon is pervasive throughout the Earth's crust, as it is a byproduct of the natural radioactive decay of thorium and uranium in rocks and soils. A heavy gas that is usually brought to the surface by the upward migration of lighter carrier gases, such as hydrogen, methane, and carbon dioxide, it's been historically linked to seismic activity. As Pulanets described in an interview with LPAC TV in April, radon emission is part of the process of gradual release of the tremendous energy potentials built up within the Earth, of which the earthquake is only the most dramatic manifestation.
When you have release of energy, which is equivalent to several thousand on nuclear bombs, so it is impossible to store this underground and stops in the one moment to release. The Earth is a living matter, and there are some processes storing of the stress, and this stress should manifestate itself in some parameters.
Okay. According to the theory of Poulinets and company, the atmospheric heating is not caused directly by the radon, but indirectly. The radioactive gas ionizes the air around it, and these ions serve as condensation nuclei for water vapor. As the water vapor condenses around these ions, they give up their stored energy of evaporation in the form of heat, otherwise known as latent heat. This process begins near the ground and continues up through different layers of the atmosphere, inducing more and more water vapor condensation as it goes along. It's interesting to note that a similar process appears to be at work in the formation of global cloud cover through the ionizing action of incoming galactic cosmic rays on the atmosphere. The latent heat released by the radon-initiated process throughout the entire column of air can be measured by satellites looking at the top of the atmosphere as outgoing long-wave radiation in the infrared region of the spectrum. In this graphic taken from the paper, you can see the thermal anomalies in a zone around the epicenter appearing in the days leading up to the March 11th earthquake, with a rapid increase beginning on March 8th. To get a sense of the power involved, consider that in this model, water vapor condensation around the ions produced by radon can release an amount of stored potential energy in the form of heat equivalent to or greater than the mechanical energy released by the earthquake itself. The chain of processes set into motion by radon emission also affects the electrical conductivity of the atmosphere, which links the lithosphere with the ionosphere through the global electric circuit. That is, the ionosphere at 60 kilometers or more above the surface can feel changes in the Earth's crust from changes transmitted through the atmosphere. The specific fluctuations in the electrically charged ionosphere above, caused by the radon-induced ionization below, can be measured by both ground and satellite-based instruments. This graph shows one of the parameters measured by satellite, the total electron content, exhibiting a definite spike near the future epicenter several days before the earthquake. Perhaps coincidentally, and perhaps not, the Precursor anomaly falls in between two geomagnetic storms during the first half of March, caused by bursts in solar activity. Previous major earthquakes worldwide have also been retrospectively studied by various researchers and shown to exhibit similar patterns of distinct precursor phenomena. As was reported on this website, there also appears to have been a group of scientists who detected very low-frequency electromagnetic anomalies in real time, some 10 days prior to the March 11th quake. But the scientists involved in precursor research have consistently pointed out that any systematic short-term earthquake forecasting will have to depend on a multiple parameter approach. Thermal anomalies, ionospheric disturbances, very low-frequency waves, microseismic tremors, gas emissions, strange animal behavior, and other precursors should all be surveyed and compared simultaneously to make accurate forecasts of impending earthquakes. In fact, in the one recorded case of the evacuation of a major population center before an earthquake, this was exactly the approach taken. In 1975, a magnitude 7.3 earthquake hit the Chinese city of Haicheng, which had a population of roughly 1 million at the time. Though over 90% of the structures of the city were damaged, the evacuation of the city the day before the earthquake spared tens of thousands of lives. The precursory anomalies that gave an indication of the coming quake included a whole range of geophysical, chemical, and electrical changes, as well as anomalous animal behavior and the appearance of several foreshocks in the days before. All in all, case studies of past earthquakes have established beyond a reasonable doubt the existence of a whole array of measurable precursors, despite the hysterical denials from establishment seismologists such as Robert Geller that anything can be learned from them.
That's why they're very skeptic. So able to convince this kind of colleagues, we need to show that first we have a good confidence in understanding the phenomena, we have a good measurements, we validate our results, and then we propose to the wide range of scientists to evaluate. So we are in the beginning of this path, but every earthquake confirms the fact that we are on the right track.
The question today is, what will it take to go from hindcasting to forecasting? The answer is, in one sense, surprisingly little. For a fraction of the money now showered on modeling man-made global warming, a small network of dedicated laboratories for precursor research could be supported, where teams of scientists could monitor data over seismic danger zones in real time rather than sifting through records of disasters that have already happened. Simply restoring funding for existing remote sensing satellites that have been cut by the Obama administration should be an immediate priority, not to speak of deploying new, easy-to-launch nanosatellites specifically for precursor monitoring. And, of course, coordination through government agencies would be absolutely necessary, since credible forecasts won't be much help without the authority to act on them. Yet, these are only modest first steps. To take the analogous case of weather forecasting, even with the advances made over the recent years in this field, the devastation being wrought by the recent surge of tornadoes shows that major new insights are needed into the fundamental causes of these kinds of phenomena. As the history of life on this planet demonstrates, there is a coherent process of development through all layers of the Earth, in conjunction with solar and galactic processes. The studies of earthquake precursors have shown a small part of this unity in the close connection between the forces shaping the lithosphere, atmosphere, and ionosphere. As experimental science expands both outward, deeper into the cosmos, as well as inward, deeper into the Earth itself, this sliver of understanding will grow into the insight needed to rise above the ancient myth that man is subject to these forces, to a realization that our destiny is to control them.